multiplication anymore. If you take a log, you actually should add those two. And then the answer becomes 5 because 3 and 2 from the top. This is a one case. So if you have taken a calculus class in college or in high school, you may have seen this laws of logarithm and the laws of exponents. So usually you learn the laws of exponents first in the bottom, but you can, interchangeably, use this laws of logarithm and exponents. So the right side here, it's just basic principles. I explained this one, power can be split. So now it's a plus here, right? X and the Y when the base is the same. If you think about negative Y, yeah, when X minus Y, you think as Y here, not minus operator, just negative Y. B to negative 1, which means actually it becomes denominator here with differentiation. No, division, sorry, division. And when the power is outside entire number, so there are two powers here. In this case, actually, you have to multiply those two power numbers. This time it's not the addition. And then power can be applied to the number inside the parenthesis, like both. So if you're not familiar with this, and try it with an actual number, very simple number. It's very obvious. In log, there's a slightly different laws, but it's also coming from the laws of exponents. In this case, we are going to use all the positive numbers. And then with a base of b, so I explained this one when there's multiplication here inside a log. And when you take the log for each part, its components, you actually have to use addition. And then there are quotient here, the x over y. So if you think about this y, so 1 over y as a y to the negative 1, that becomes obvious here. The operator becomes minus instead of plus. So without understanding, you may have memorized this one. Oh, in this case, and it should be negative in the past. But now think about why it's negative. I showed you this one very beginning. So the power can come in front, right? So R comes out here, R. But when the base is different from the base of the exponentiated number, it stays. When it is the same, it just becomes, 1. So you only have R per definition, but in this case, only power comes out and then stay in front, and then this log part stays as the original. So it's nothing much to memorize, but we're going to use this log in later. We're going to see why we need to know the log and when we can use the log. But that was a very basic concept, and then we're going to move to the compounding concept in financial mathematics. So if you have taken corporate finance class or any other finance classes, you may have heard of this concept. The first, now we want to know nominal rate, term nominal rate, or what is actually nominal rate. The word nominal, according to the dictionary, and then means a certain name only, comparing the name of a person or a certain subject. That's what, and the nominal. So in macroeconomics, we use this term, a nominal rate. and also sometimes real rate and compared to the nominal rate. In finance, we use more term called effective rate compared to the nominal rate, because the compounding concept is important in finance and time value of money. So nominal rate in finance and in generally in economics and also real world, it's just the rate in the name only. So what does that mean, name only? So it indicates, it shows the rate, but that's actually not exact the rate we're gonna actually pay based on. So what is the actual rate or actual value you're gonna pay? And then so we want to know, and then we need to understand a compounding concept. So let's see two examples considering different periodicity. The compounding concept comes with then different periodicity and period rate. So our basic assumption about the world is yearly and the annual rate. So that's what the nominal rate usually shows you. But if a certain investment or a certain bank account, that if you put a money in there, you get a return. But this return is given to you every month, let's say at the end of the month. And the percentage is given to you as a 1%. And then this is called interest or investment return. But this interest will earn interest again because it goes back to your account, and then it stays. If it stays there, right, our assumption is we're not taking out that interest earned. That interest we're gonna earn interest again. So it is called a compound. So compounding means in earning interest on interest. That's gonna happen 12 times for the year, right? Because there's 12 months. So at the end of the year, the amount of interest you earned is not just 12%, because it's more than that. If it's, for example, the interest was paid only once at the end of the year with a 12%, that, let's say $100 of investment, you're going to get $12. So 12%. But if $1 is earned at the end of the first month, and then that $1 will earn, it doesn't stay like that. It will earn interest again in the second month, and then that will earn again in the third month. You're gonna keep growing. So you can imagine it's gonna be actually a little more than $12. So how can you calculate that, the actual amount of money in terms of a percentage? So you add that monthly, where is this? Okay. You add 1% to 1. The reason we have 1 here is because we want to calculate the principal, and then power of 12, which means it's multiplied by 12 times. So think about it, only 2 months, right? How do you calculate actually how much you earned in 2 months? Is 1.10 times 1.10. That's the amount you earn plus principal amount. And at the end, you subtract 1 to take it out the principal amount to calculate the what is actually interest only, the percentage. If you calculate this one, let's say in Excel, 1 plus 1%. Well, minus 1 gives 0.127. In percentage terms, it's 12.68. Now, there's another investment or bank account that gives you 3% return every quarter. This needs to be a little corrected. So in your file, it also has an error. At the end of the what if instead of 1% every month, you're gonna get 3% return at the end of, I would say, easier term, at the end of every quarter. So quarter, 4 times a year. So 3% per quarter, and that translates into 12% a year in a nominal rate. So this is what nominal rate actually means. The first investment also has nominal rate of 12% because 1% per month, and you just simply multiply the number of periods for the year to calculate a nominal rate. So two investment case, nominal rate is 12%, the same. But the second investment, your money will compound 4 times because every quarter you get a return, and then that's compounded. How to calculate effectively how much you earn on this one for the year? The calculation is 1 plus that 3%, right? Your file has 12% with a power of 12. Just please correct that one. It's 3% and the power of 4 and minus 1. And then if you calculate this 1 plus 3% power of 4 minus 1. 12.55%. So if you compare nominal rate between these two investments, 12% same. So you can't tell which one is better. But if there's a compounding with a different frequency, you see effective rate for the first investment, which has more frequent compounding, has higher. The rate is slightly higher, right? I mean, both of them have higher rate than 12% of nominal rate. So effectively, you are earning more than $12. But when the frequency of the compounding is higher, even though the nominal rates are the same, the effective rate is higher. But that's how you can compare different investment methods or bank accounts, usually savings accounts that pays interest, by calculating the effective rate. It's the same when you pay interest. So nominal rate is used, is by law actually, in any lending product. The credit card is a lending product. If you take a loan, that's a lending product. Lending from the bank, right? And they are supposed to indicate what is the actually the nominal rate. So you can see like a credit card, rate is like written, 25% or like a 20%. But that's not exactly the amount you're going to pay as an interest, because there is compounding involved and then it's not really mentioned clearly. in the documents. So but the compounding is basic principle in finance. It's widely used unless it's stated otherwise. Unless the document or the loan contract says, oh, there's a simple interest, which the interest does not compound. That means you just get straight, nominal rate, but that's very rare. So one other correction here is in the second line. We can take 3% quarterly rate and multiply by 4, not 12, to get the nominal rate of 12%. So please correct that one in your file. And as I said earlier, nominal rate can be calculated from periodic rate by just multiplying, the frequency of that period in the year. So we multiply 4 to the quarter, right? Because there are 4 quarters, and then 12 for the month. But the other way is the same. How do you calculate the period rate? You just divide it by the number of the periods. So 12% in nominal rate is given, right? Period rate for the quarter is 3%. So this is very straightforward. So don't be confused with effective rate, right? So this period rate and nominal rate are just like very simply, you can convert between them. So this is an important concept to understand the time value of money. It's related, which we move to the next tab. The time value of money and is the basic principle and the basic assumption in finance. What it says is $1 today has a different value from the dollar tomorrow. Same, it's dollar from yesterday. Yeah, they all have different values. Why is that? It's not because you change it, or you just hold it as single dollar bill in your hand. There's an assumption of earning interest. So in finance, you assume the money can be invested and then earn interest without a risk. So that is what the time value, because time actually add the value to the money. So let's see how mathematically that's expressed. The interest is added, and then how we can calculate that one, considering the compounding and the discounting. The discounting is actually the opposite side of the compounding. So here, the notation P sub 0, subscript 0 is the amount of money at the beginning. So initial principal or initial investment amount at times 0. So the next period, the amount of money we're going to have is from the initial amount plus certain interest rate is applied to set that principal here. Let me write again. R1 is interest rate for this period, and that multiplied it to the principal. So this amount total is interest earned, right? Plus principal is the amount in the next period, which is at period 1 in timeline 1. And then if you move to one more period, this period is it's a compounding period. And then this time the interest rate could be different, or it could be the same, but let's say R2 applied to P1, that amount at time 1. This total amount is interest earned for that period is added to the previous amount, P1. So you can keep going in this way, but before moving on, so you see it's a common factor here, right? P1 and P1. So group that, take it outside of parentheses. So group 1 plus R2 right? So this way you replace P1 as well. P1 was expressed in this way. If you group this P0 times 1 plus R1. Because P1 is this, right? You plug this one into this. That brings here. P2 is starting from P0 times 1 plus R1, the interest rate from the first period, and times 1 plus R2, interest from the second period. So you generalized this concept. At time t plus 1 in the future, why t plus 1? Because we want to start from t, the one at this time. Okay, so let's start from the right side then. The amount at time t, you just add interest by multiplying 1 plus r sub t plus 1. This is the interest rate for that period. Then we just get the amount, next period amount. So now, if you generalize further, p sub time capital T, this time t stands for just any time in the future, and start from principal amount, right? Then you can imagine you have to multiply all of this interest factor, the compounding factor, 1 plus R1 times 1 plus R2 is all the way to time I here. The I goes to T, right? This capital what? Pi, it is an operator. This is a multiplication. It's similar to sigma is for the aggregation. So if we assume this interest rate is the same for every period, right? Let's say it stays as an R1, like here. This multiplication becomes actually power, t times, right? So now you see the amount in the future at time t, assuming there's a compounding and the interest rate has been the same for every period, starting from initial investment amount multiplied by this factor, this compounding factor, this whole thing, right? So this is the expression for the future value. And then we call this P0 in initial amount the present value. The present value became future value with the compounding. Now, if you think back, how do we find the present value when we know the future value? That is discounting here. This factor, right? Look at this, it's different. It's I'm gonna highlight this. This part is negative t. Power is negative t, which is effectively what? This is 1 over 1 plus r to the t. Or you can think of it, this is actually dividing by this. So future value multiplied by discount factor. Now it's called discount factor. Or future value divided by this gives us the present value. So finding a present value from the future value is discounting. We're going to use this term, a discount factor or discount interest rate to point out this R, interest rate. This could be a compound interest rate in this perspective. But the other way, it could be called a discount rate. This whole thing is called the discount factor, but this R itself is called discount rate or interest rate. So this is a concept. In finance, you see this one in valuation concept. When you value a company or the financial securities, basically the valuation is discounting the future cash flows to calculate the present value of all the future cash flows. The discount rate could be different for the period or for the different instrument or different purposes, but basic principle is discounting the future amount. So the practical issue becomes actually finding the future amount of how much it is, also which interest rate is the right discount rate. But this is the basic, the fundamentals for the time value of money calculation. All right. Now, moving on to the combinatorics. Oh, before we move, actually, there's another video linked here, time value of money. If you're not familiar with this concept, and then I recommend you to watch the time value of money video as well. Now, the combinatorics. So combinatorics, it sounds complicated, but it has a practical use in finance. So let's see some examples first to understand how the combinatorics work. The word train that has 5 letters, and they're all different. How many orders can we make? So if you rearrange these letters, right? How many word can we make by rearranging these 5 letters? That's the question. So you may have seen this, right? And you may be familiar with this one. In this way, you put this places here. What's happening? Sometimes this does not work. Yeah, like this, right? You think about it this way, and then you think about the first place, what letter can come? Any, right? So the possibilities are the 5 different letters can come here. So once you use one letter, right, there are only 4 choices left. So you can use 4 letters here. Of course, now it goes like this way, right? 3, 2, 1. But these possibilities needs to be multiplied. Yeah, these are product of these numbers to calculate all the possible combinations. So this is gonna be the answer, 120. But there's a way to calculate very simply, right? This is called a factorial in mathematics. So 5 factorial is exactly like this. You have a product of all the numbers, you know, starting from the 5. Now, there are 5 horses in the horse race. If you want to check only first to the 3rd place, how many orders can we see? And if you care about first, second, and 3rd place, which horses come in? Of course, the 3 horses are different. This time, it's not going to all the way to 1. You start from 5. Let's say in here in the example, just because it's 5, let's use the same example on top, only for these 3 spots, right? So first place, any horse from 5 can come. Second, now it's 4. Third, 3. Remaining 2 places, we don't care. So the total possibilities actually becomes only 60. It's important to understand intuitively how you calculate, but once you understand the intuition behind, right, we want to know how to calculate mathematically quickly. It's called the permutation. So there are 5 bases, and then you choose 3, but you care about the order. Yeah, right, order. Is it horse race order? So that's how you can write down 5 permute 3, or you write the permute function in Excel. And look at the formula window in Excel. Permute function, and then in parentheses you type 5 and 3, and then gives us a 60. Mathematically, this is called a 5 permute 3, right? So 5 here, and let me write down here. 5 permute 3. There's a formula, right? But I do not recommend to memorize the formula. If you understand the principle, right? First, we learned about the factorial, because there are 5 horses. You want to know all the possible combinations, but actually what you don't care is 2, right? Because you want to know about only 3. How do you not care about 2? That means 5 minus 3 in this case. So 5 minus 3, right? And then permutation. This one gives actually 5, 4, 3, product of those. That becomes 60, right? That's what is this formula actually does. Okay, now order with repetition. We want to make an order of the word moon. There are 4 letters in there with 2 O's. So how do you count what unique words you can make out of this? So it's slightly different, right? If O's were different, it could be what? The 4 factorial, but you can think of it like O1 and O2. They're different than 4 factorial. But when the 2 letters are the same, you got to remove that duplication when you count it, treating as the same, different letters. So that one, the factorial 4 divided by factorial 2. Think about it, why that's the case. Factorial 4 is just a regular order. You want to divide it by the number of the cases you actually made the duplication. But that's the actually factorial 2. That's why you divide it by that. There are 2 O's here, right? Again, I'm emphasizing it's important to understand this logic, and then the calculation itself is pretty simple if you understand the logic. But if you try to memorize all this, like let's say, oh, when do we use permutation? When do we use the combination or factorial? And then try to use the formula you memorized, it's going to get very confusing. You cannot understand well, and you cannot explain, of course. Next topic, I already mentioned the combination. So in order to explain the combination, look at this letters, 3 P's and 3 U's, picked or unpicked, or next case, that's the P's and Q's. So only 2 letters, but it's repeated, 3 times each this time. How can we find out how many orders you can make? If you imagine this one, they're all different letters. Of course, yeah, there's 6 factorial. But look at this. It's combination 6 and 3. And mathematically, you write down 6 combination 3. This is how you write down. So this is the same. It's very similar to choosing you choose 3 out of 6. So oftentimes it's read 6 choose 3. But because the repetition here, right? You gotta actually divide it by that possibilities, right? You did in the moon case, right? So this time 6 factorial up top, in the numerator. But how many times are duplicated? 3 of them here, okay? PPP, you divide it by that. But also there's the UUU. If you see this, actually, and then look at this formula, this above, right? This is a way to express this n choose k in this big parenthesis, this concept of this binomial coefficient we call, and this is n choose k. Formula you may have seen this like this, n factorial divided by k factorial times n minus k factorial. If you had tried to memorize this one in the past, you remember what was confusing things, right? You didn't understand why I had to memorize all these things. Now you understand, right? 6 possible cases, but you gotta divide it by this, but this works like that. You choose 3. This first 3 is matching k here, and the next 3 here is actually 6 minus 3. That's why it's become 3. If you think about this case as P and Q, or even 0 and 1, or true and false, or success or failure, when there are 2 possible cases, it becomes a binomial case. And we're going to talk about this binomial distribution later a lot, because when there is only 2 possible outcomes in certain event with a probability of a success or a failure, right? There are 2 components, so you need to know how many times you can actually succeed out of how many trials, and with what percentage, what probability, right? Before getting there, the one more example, because in this example is coming from the option pricing with the binomial tree. In this binomial tree here, you see the S0 is this case, commonly it's a stock price, but it can be underlying assets price. Can have a binomial tree which shows the price can move up or down in a certain defined time period, right? For now, we're not going to talk about that much, right? It can be very short or a long time period, but you move in a certain time, the price moves by this factor, U or D. So U is up or D is down. And in these 3 time periods, stock price got to here, S sub 0 times D. So binomial tree is showing only 2 possible cases, right? So up and down will always end up in the same price as down and up, because this ratio of up is always the same. The ratio of down stays the same. I'm not saying they are the same. These U and D are different, but U stays the same in every period. So how many passes can we find starting from S0 to get to S0D here? You can manually check, right? Up, down, 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 up, down, 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 up. This is the only possible 3 ways. You cannot go up twice and can get here. So this question like virtually becomes the same question as, okay, you have UDD, 3 letters. How many possible orders can you make? So this one becomes suddenly, right? This what? Now 3 choose 1 or 3 choose 2. Actually, that's the same. 3 choose 1, 3 choose 2. Think about it, why these are the same. So you check on your own. So now the binomial distribution, the question I already mentioned earlier, what is the probability of k number of successes out of n trials? So the basic setup, you need some context. We have a case, or we assume the certain event has only two possible outcomes, but the outcomes doesn't have to have the same probability, right? You can have a high success rate, but either success or failure, right? Or up or down in this case, right? But if you can assign a probability to that success, how do we calculate what is the actually probability of have multiple successes out of total trial, right? That is the concept of the binomial distribution. And then we want to know probability. So here, some people may call it a formula. I don't like calling it a formula. You got to understand how this is created. There are n trials. By the way, these are all these statistical terms, like trials, but you can think about we have n possible cases, but we want to check success. I want to know 10 times. Let's say we have 10, certain events. We're going to see this case like a bond, like there are 10 bonds, either default or non-default. That's a very typical example, right? There are 10 bonds. We want to know what's the probability of like a 2 bonds default. So when you say 2 here, k, right, you need to know, we're talking about the default in this case, right? We define the k for the default event. Even though we say success, it really depends on what you just defined and how you define. Probability, you give the probability, you can give a number, but let's just use a p here. And then this 2 should go to here. Oh, sorry. Erase. Here. 2. Why is that? Because p with a probability, this event happens twice. So that's why you have to have a product here. But we also got to consider what is not defaulting, which is failure in our definition. This part, oftentimes we call it Q, 1 minus P. P, whatever percentage you give, 20%, 30%, Q becomes 1 minus P, like in this case, 80%, 70%. This non-default also should happen for the remaining bonds, right? Which is 8. Remember what we're checking, 2. That 2 goes here, but this 8 is become 10 minus 2. This 2. So this is the calculation of the probability in this all trials. In the discrete case, right, like this, in discrete variable, which we talked about in the bond case, in the real life case, and especially in finance data, we see the discrete variables. So it's going to be the probability of the probability mass function. I'm sorry, not the probability of mass. It's actually just the probability mass function. In continuous variable, you heard this term, probability density function, in short, the PDF. This is sometimes called the PMF. And if you have taken the statistics or mathematics, right, then in short, PDF is used widely because it has a mathematical expression. But binomial distribution, right, this is the case. We're gonna have a chance to see the actual calculation with a bond in the next file. So we're gonna move to the file, class file 2. So it's time to open the class file 2 for you. Now I'm going to share now class 2 file. Yeah, if you guys don't see the class 2 file, let me know. I just shared a new file. So let's talk about the time value of money a little more. Compounding tab. So nominal rate here. Let's start with the example, 10% for the year. And below, we give different periods, semi-annual, quarterly, monthly, trading days, and calendar days. So semi-annual means every 6 months, interest will be paid to you or you pay interest. So that's the compounding period. Every 6 months, that makes it twice per year. What is the effective rate for that? Let's start with the simple one. So yeah, I know everybody's looking at this formula up top in red, but before talking about the formula, let's understand how we can calculate the effective rate. We already saw this one, by the way. Oh, wow, this looks more complicated. Actually, if I get out, first of all, we gave this, sorry, the data array, right? You should have heard this term before in Excel. We gave a name to this data array, periodicity, here in the name window, you can see here, so that we can use the entire data set without changing the rows. So this is a periodicity. We also gave a name to this. Is to check rate is the name. So what do? Instead of pointing each cell, we just use that name. 1 plus rate. So now it's 1 plus nominal rate, but the nominal rate is divided by periodicity. In this row, that is 2. So 5% is used here. So 1 plus 5%. That is the period rate, right? For this 6 months. So 1 plus 5% to the power of periodicity, which is 2. So basically, this is the same formula as I showed you earlier. And I write down here this one. This is basically 1 plus 5% to the power of 2 minus 1, right? If you recall from the previous file, we calculated this 2 investments case, right? Remember? So same, quarterly compounding. There are 4 quarters in a year, so this formula stays the same. The beauty of using the data array by assigning the name, you don't have to change the formula in each cell. It just point this the cell by using name, and the @ sign just point each row in this data array. So it looks like all the same formula, but it's using the different data points here, right? So let's say here in calendar days, so this is typically called a daily compounding. There are 365 compounding period in a year. So calculation here, let me show you here. This is basically 1 plus 10%, you divide it by 365. What is this? This is the period rate to the power of what? 365 and take minus 1. It gives this percent. So these are all effective rate in column D. And you can generalize that one and create a formula on your own. How do we calculate the effective rate? See, here in the red, 1 plus R, which is nominal rate. R is nominal rate. N is what? Frequency of compounding. That N also goes to the power outside. This is a compounding part. And just subtract the 1 to see the percentage, the return only. So like this whole calculation, we used this formula in an Excel. But look at this. As periodicity, which is the frequency of compounding, increases, your effective rate increases. It's intuitive because you compounded much more times in a year in the same time frame, and then you will earn more. But you also observe as we increase the compounding frequency 10,000, 100,000, million times, then the percentage, effective rate percentage converge to a certain number. Not exactly the same, but if you graph that below, right, the effective rate you can see increases, but it converges, it reaches to the certain level. So here I'm trying to explain the concept of continuous compounding and the continuous rate, which is theoretical. So if you make the compounding very, very frequently, right, less than a second, less than a nanosecond, and then let's say it becomes continuous. It's a theoretical concept. It's continuously compounded. And then what would be the effective rate? How would you calculate that one? The textbook should have been mentioned in the last seminar, because this class has a textbook and the seminar is using the same content. So there's a textbook. It's called the Mathematics and Statistics for Financial Risk Management. In the textbook, it shows the formula, right? And it has some explanation, but mathematically, we want to see how we can get to that formula. E to the nominal rate minus 1. Yeah, here, Excel, right? EXP is exponentiate function. So basically becomes what? This one is become e to the 10% minus 1. But why is this is the case, right? How do we know? It requires a little bit of explanation here. So the E is the, I said at the beginning, it's the Euler's number, right? In mathematics, we use this one. If you look at this compounding formula, right? 1 plus nominal rate divided by number of frequency, but this frequency goes to infinity right now because it's continuous. When this goes to infinity, where is this? This one goes to infinity. This one goes to infinity. If you have not learned the calculus, it's not easy to understand what is happening, right? Denominator becomes really, really large, goes to the infinity, but the power also goes to infinity. So look at the right side, there's a little conversion happening. So starting from this definition of E, mathematically, E is defined in this way. Yeah, here, if I move to the right side. Exact definition is here, using the limit concept. There's a limit that when the n goes infinity, right? See, 1 plus 1 over n to the power of n, that is actually E, Euler's number. sometimes called the Euler's number in the US. This is the definition of E. So, but we have a very similar form in our effective rate calculation, 1 plus R over N instead of 1 over R. So let's change it, the variable, by saying, let's say N over R is M. In that case, we can change N is what? Actually, R times N, M. So in this case, when N goes to infinity, M also goes to infinity, and vice versa. M goes to infinity, N goes to infinity. So now we change it. 1 plus 1 over M to the M. You see, this form look the same as definition of E. And then change it. Instead of M, now is N over R here, N over R. If you're not familiar with this, right, do it with a pen and paper. But in this conversion, right, this whole thing actually becomes R, E as N goes to infinity. We skipped all the limit sign here by assuming N goes to infinity. But this R stays outside still. That's why it becomes E to the R. So there's a mathematical proof for this one, but many people will just memorize continuous rate, E to the R minus 1. R in this case is a nominal rate, but continuous rate is the highest rate you can get as an effective rate. And it also it's used widely in pricing certain financial instrument. As I said, continuous compounding is not the real compounding. It's a theoretical compounding. But there's a beauty of using continuous compounding in mathematics. And pricing gets very complicated in the real world, especially option pricing. So continuous compounding is used in the mathematical formula and the calculation to usually find the benchmark price, because you need a certain model to value and the price in the financial instrument in finance. And the risk, as a risk manager, also you need to validate that one. And then, so you need to understand this, what it is. But we covered this continuous rate. Now we're going to move to the yellow tab, which it becomes an assignment in the class. But for us, we're going to cover model a bond. So the question, the right side is instead of writing everything I already wrote before the seminar started. The question here is model a bond manually in Excel. Model a bond means actually you calculate the bond price by calculating each payment. Bond has interest payment, which is called coupon. If you buy a bond, you receive a bond, the coupon interest. If you issue a bond, let's say you work at a company that issues a bond, you also may need to calculate how much you're going to have to pay to the bondholder. But either way, the modeling a bond is showing this all payments or interest for the period, and finally what's going to be the value, which means the present value oftentimes. Do not use pre-made Excel function. There are pre-built Excel functions for bond calculation. So assume annual payments. The information is given here. Face value. First of all, if you're not familiar with what the bond is, or all these concepts about the bonds, is this possible? You may not have the background in finance. I strongly recommend you to take a finance class and plus a seminar. So in face value, $2 million, yield to maturity, YTM, 3%. That is gonna be the actual interest rate for this payments. So we're not going there deeper in this class. And the coupon rate is the interest paid. It's nominally. So you can think of it as a nominal rate. A maturity 10 years. So we created this schedule, payment schedule. T column, time 1 to 10 every year. First year to 10th year. Coupon amount. From the face value, coupon rate is applied. Because this is an annual coupon, you just get $80,000 every year. In reality, the semi-annual coupon is much more common, so you're gonna get like a 40,000 every 6 months. But in our example, 80,000 for simplicity. This coupon amount is the same every year, but this is a nominal amount every year. It depends on the time. This value is different. This 1 to 10 is, oh, sorry, at that point of the time, but we want to know the value right now at time 0. So you need to discount this amount using present value factor or discount factor to get the present value. So how do we get the discount factor? So 1 over 1 plus what? This time discount factor is yield to maturity. And then denominator has a power of the number of compounding. In this case, it was first just 1, but in the middle of the year, it's not going to be 1. Like 5th year, you have to discount 5 times, and then this power works as 5 times. So if you multiply this present value factor or discount factor to the nominal amount here, you follow my Excel formula, you get the present value. The present value of this $80,000 at the end of the first year is $77,670. You calculate this every year. So let's see the 10th year. Oh, sorry, moving. 10th year, first of all, present value factor, right? You can imagine just power has changed in the denominator, right? Discount rate is still 3%, but to the power of 10. So discount factor is much smaller compared to the year 1. So we get the present value of only $59,000 for actually this $80,000 nominal value, because it's discounted 10 years. Now, this present value, remember, present value is value at the present time. All these 10 cash flows, this 10 cash flows becomes this. This sum of this is the present value of all the coupons. But one last cash flow is the principal amount. At maturity in 10 years, you receive this $2 million of face value because you bought a bond 10 years ago. Now that amount also needs to be discounted for 10 years. Same discount factor here, right? So you multiply that, you get 1.5 million. Bond value at present time is sum of all this present value of cash flows, right? Including the face values, present value, which is sum of all the values. So 2.17 million. This is the value of the bond. I'm not saying this is the price traded on the market. So that's slightly different. the bond concept will be discussed much more in the finance class, but I want to just say one thing. When you think about this bond pricing, draw a timeline. Think about it this way. We want to get the present value at time 0. That's what we're doing, what we did here. Present value of everything for this time 0. This is important. But you got to check the cash flows here. Here, time 1, 2, all the time at 10. 80K plus, right? Principal, face value. This is not a future value, face value. Also needs to be considered. That's the good practice. Now, rule of 72. It's just a interesting rule used in the industry. Usually, you search the web by yourself. But what is the rule of 72 is how many years does it take to double your investment? So that, and then you can use the rule of 72 and then get the approximate amount, a number of years. So when you have percentage return, that percentage number, you can use it, and you divide it by that number, divide 72 by that number. Let's say you have 8% return for the year. How many years does it take for you to double the investment? 72 divided by 8% means 9 years. So that is the rule. So I want to show you mathematically why that is not completely wrong. Oh, sorry, I pressed the wrong button here. Using the time value of money concept, right? Starting from here, P0, principal amount, and then 1 plus R, there's a certain interest rate. And then we want to know this T, time T, how many years, and then we can make 2 times principal amount, right? 2, right? Double. In order to get the T, it's time to take a log, both sides. P0 is gone in both sides. Take the log, natural log, with the base of E. ln stands for that one, log. And then I told you T can come down. Power can come down here. So power comes in front of the log. Log 1 plus R equals log of n, log of 2. Because our goal is finding a T, you divide this log of 1 plus R in both sides. So T equals log 2 divided by log 1 plus R. Okay, if we know the discount rate, we can find the T. So let's find it. Interest rate, yeah, we try 1% to 12%. We're gonna try just, and then calculate T according to the formula. You build a formula. ln is a formula for log, natural log. 2 divided by 1 plus this rate, 1%, or 2%. You keep using this. You get 70. Well, you do 1%, you take 70 years. But what does rule 72 says? 72 divided by 1 gives you 72. So what's the discrepancy between this mathematical result and the rule? It's 2.3 years. Okay, it's a bit of a difference, but increase the interest rate, right? Let's say here, I gave you 8%, right? If you use a formula with 8% in R, you get 9. Rule of 72, 72 divided by 8, exact 9. By the way, this is not exactly 9. That's why there's a slight difference here. And so it's almost the same, right? So let's graph this, the difference. So rule of 72 is given orange color. And then T is actually mathematical calculation. This gray line shows the difference only. Difference goes down. There's almost no difference around this 8%. And between like a 5 and 11% range, when the interest rate is like that, rule of thumb, the rule of 72 is it's not that wrong. So without the like log or mathematical calculation, you can quickly say how many years it takes to double your investment. That is a rule of 72. We just saw the one use of a log, but I will show you another use of a log here. And we're going to continue this life annuity in the next week. We have a data set here. Yeah, 11 data points. There are 2 data sets, X and Y. The paired data set. And then we want to graph these. So I don't know, you guys know how to graph this one. Usually you select these 2 columns and then insert and graph. But we already have the graph here. So if I choose this, it shows graph like this. The Y values here, as you see, they're E. This is a scientific expression of very small numbers. You see, oh, sorry, I said small, it's very large numbers. Small numbers has a negative, but you can have like a positive, but this is showing the powers. So Y values and X values in a very different scales in this case, right? If I expanded this one, right? Y you can see is 222, but this suddenly became really large numbers, or it can be very small numbers. In X, it's just a, 1 to 30, but Y varies like from 2 to like millions or 100 million. When the 2 data sets are in a very different scales, right? If you draw a graph and plots, sometimes you can see like you cannot see the difference in this Y values. But let's see, you take a log value of this one, right? It's small, but even the very large numbers, the log value becomes small. But it's also depending on the base, right? It gives a different value. This is a base of 10, this is base of E. But if you change to this, let's say, now you see relationship much better. Or this, similar, but you can still see the relationship between X and Y compared to this. So this is a one usable log scale because you can scale differently using log. So there are many use of log. So that this is the last part of the today's seminar. We're going to continue next week, but also I'm going to share the link one last time. Seminar files all saved in this Google Drive. We just use the class 1 and 2 files. We're going to continue these 2 files and then finish class 3 next week as part of financial mathematics, financial math 2 next week. All right. Any questions? If not, thank you for attending today's seminar. I hope to see you guys next week. Okay, bye.